Yeah, so for sodium plus it is 1.1. For F9, F minus you were correct.
Which was, what did I write?
0.8.
Well, 1.125, and then I had it wrong for oxygen, it should be 1.133.
No, for fluorine it's
Fluorine,
9 divided by 11, which is 0.82.
0.82.
And then 8 divided by 10.
I would get 9 divided by 11.
Yeah.
Jen-
It should be 9 divided by 8, so that's why I got,
Okay, so
Would it be 10 though, because you're adding an electron?
yeah,
yeah.
so this will be 0.9.
0.9. And then
Oh,
right below it would be
I did
0.8.
too. Sorry, I meant 1. Sorry.
Yeah.
Jesus Christ.
Yeah, it was a simple, and we all did mistakes. Okay, that's fine.
Where is the 9 coming from?
The atomic number.
So it's a Z by number of electrons. So Z was 9, and what's the number of electrons?
10.
9 plus 1, because it got an electron, right? Now, can you guess which is the biggest, which is the smallest? Just don't think about numbers. In your head, think what happens when you lose electron and you gain electron. It's easier to think when you lose electron. So compare these two and tell me which of them is smaller. It's easy, easier than these two. Na plus is what Courtney says. Who concurs?
Which is smaller?
Which is smaller, yeah. So what you do is you write the configuration. Which is smaller?
Between those two?
Yeah.
Plus?
Why?
You're losing the electron.
You lost your electron, so there's no one in 3s. So there is no 3s if you think of that way. Because the space is always there. So if it's an atom, even if it is sodium, so there will be 3s and then 4p and whatever, things exist. But what do you see existing? When you see because you see the orbital concept is a very theoretical concept. It doesn't exist in nature, right? So when you are able to see the electron in sodium in that region, you call it that electron is in the 3s. You said the 3s is occupied because you anticipated if the electron came in, that would be in the 3s. But if that electron is not there, can you see that electron? If the electron is not there, so that thing went from 3s to just 1s2, 2s2, and 2p6. So what was 3s has now confined to just the 2p6. So basically, there were 3 shells, and now there are just 2 shells. Shell 1 and shell 2 here. So which one should be smaller to you when you're seeing at it, when you're looking at it? The plus, because that 3s is not there, you cannot see it. Then, can you just guess, is there a relationship between, can you just tell the effective atomic number has some relationship with the size? So what is that relationship? It is directly proportional or it's inversely proportional. And by that I mean, will increasing z increase the size, meaning directly proportional, or increasing z star will decrease the size, meaning inversely proportional. It's inversely proportional because you went from 1 to 1.1 and your size decreased. So an increase in the effective atomic number means there is a reduction in size. And what is effective atomic number then? It's the pull. It's how, if you can just think that number in terms of a physical thing, is the pull. If your Z star is more, that means there is more pull. And if your Z star is less, that means there is less pull. Why is there less pull? Or slightly more repulsion than in F. So F minus has a Z star of 0.9. What is the Z star of F? 1. Right? So any element will have a Z star of 1, basically. And any cation will have a Z star more than 1, and any anion will have a Z star of less than 1. And if Z star means the general pull, if 1 is like the normal amount of pull, a 1.1 will mean more pull. Pull between what? The nucleus is pulling the electrons. If you're pulling the electrons more, you're shrinking it. That's the general concept. So why did it decrease? Why did the pull decrease? You added that electron, and because you added that electron, there is a But now I want to trick you guys. Here's how I will pose a question. The force of attraction that we first discussed, the electrostatic pull, right? It was something like a constant Q1, Q2 by R square. Q1, Q2 is like if we want to understand the pull between the nucleus, which is positively charged, and the electrons, which is negatively charged, this and this, so the number of electrons are increasing. So isn't this increasing? Shouldn't that mean you're pulling the electrons closer to each other, like towards the nucleus?
Yeah, but R is increasing
because of what?
it's the
rate. It's at the rate.
The R is increasing. The R is the distance between the two charges.
electron that was added, so it's the furthest most from the nucleus.
That's fine. But since you're adding an electron, there's a pull that is happening, should increase, right?
But don't for like electrons repel each other?
Right. That's what is happening. So when you made that atom into an anion, they started repelling each other. And that is the reason for that increase in size. Because the electrons are much closer than each other than the nucleus, right? So think about it like that. Okay? So the electrons start to repel, and that is why there is an increase in size. So first, let's compare the cation to its original parent element and an anion to its parent element. What will the cation do? Like, what's the relationship between the cation and the parent element? Is the size increasing or decreasing? So when you have a K plus and a K, or Mg2 plus and Mg, what's the size relationship? So you have Na and Na plus, you have Mg and Mg2 plus. Which of them is bigger in size?
The original.
The original is bigger, isn't it? Think about it. Forget about the numbers, just think about it. What's happening? You're just losing electrons? If you're losing electrons, essentially you're losing the shells. Even if you're not losing the shell, let's do Mg plus. So the shell remains the same. So Mg is 12, so it's 1s2, 2s2, 2p6, 3s2. Mg plus is 3s1. Because of so you didn't lose a shell. You lost an electron, and that means that the electron repulsion that was happening here is now decreased. And that's why there will become a little closer. So Z for Mg is 1, and for this is 12 by 11, which is more than 1. Right? So Z star of Mg plus is more than the Z star of Mg, and therefore its size is less. This number is just putting you, it's making it more quantitative, but the feel is the actual thing. If you just sense it, that's the actual thing, right? So the size is, so here's the thing that you should note. The cation is always smaller than the parent. And the opposite, the anion is always greater than the parent. Okay? This will become important because now when you become smaller, you start fitting into a smaller space. And these fittings will be important in geology, because when you have all these different elements trying to fit into different crystal lattices, making minerals, things like that, this will become important. The sizes. Okay. Now, when the species are isoelectronic, meaning they are same number of electrons, in all these, the number of electrons is 10. So when you have same number of electrons, when you have isoelectronic species, then based on the Z star, you can predict a size distribution. So in here, all of these have the electron 10 electrons. So which is amongst these, which is the biggest in size? Which has the smallest Z star? Right? F minus, then Na, and then Na plus. This is size. Not a very difficult concept, but an important one. Okay? Any doubts in that concept? I hope it's clear. Okay. Jocelyn? It's fine? Okay. I want you guys to think about two things now. The nuclear charge and the number of shells. Okay, this guess is out. We know that for isoelectronic, the size is inversely proportional to the Z star. This is how we write. So directly proportional inversely. Have you seen this notation before? Okay, cool. Now I want you guys to think about two things: nuclear charge and number of shells. What is nuclear charge? The charge on the nucleus, which is positive. So basically I'm talking about what? Give me a number. What is nuclear charge? How can you represent nuclear charge through atomic number? So basically I'm talking about Z. And I'm not going into the history of periodic table, right? So I'm not going into that. So periodic table was different through ages. So in 1800s, people were trying to figure out trying to group elements. So there was de Brognie's law of triads, in which de Brognie was trying to bring in three elements together, and he would arrange them in increasing order of their atomic weights, and then he would figure out the one element which has the average atomic weight also had average physical and chemical properties. So that was the de Brognie law of triads. Then came the Newland law of octaves, in which again, like, tried to arrange these elements in increasing order of their atomic weights in 7 series. So there's relationship with the musical octaves, so it became the Newland's law of octaves. Then Mendeleev came and tried to arrange elements in increasing order of atomic weights, and said, so Mendeleev's law and the Mendeleev's periodic table became that the periodic functions or the periodic properties of the elements, or let me restart. The properties of the elements are periodic functions of their atomic weights. That's what he suggested. So he arranged everything. You must have done all these things. I'm not repeating those things. But the newest one is the Moseley's law of periodic table. So when you see the periodic table, you see that the elements are arranged in increasing order of atomic numbers. So that's the way it is arranged. So you go from atomic number 1, 2, 3, 4, and that's. And we'll see that there is a periodicity in their properties. So that's what basically the modern periodic table does. So it arranges elements in increasing order of their atomic numbers. That's what it does. If you're a little rusted on that, go and watch. There will be millions of videos. Okay, I'm not getting into that. So nuclear charge should be easier to predict. So whenever you go from left to right in a periodic table, what is happening to the nuclear charge? Is it increasing or decreasing? It's increasing, because that's what you're doing. You're filling it up. So it's increasing. And what is happening when you are coming down in the period, in the group? It's increasing, right? So no worries there. Number of shells. What's happening when you're going from this to this? What's happening to the number of shells? It stays the same, because that's the property of the period. The same period is going to have same number of shells. That's the definition, right? That's how it is arranged. But what is happening when you are number of shells increases, right? So keeping in mind these two things, now we will try to understand these different properties. So the first is atomic size. Think about it and tell me what will happen when you have a cheat sheet, which it's very dense, but it will make more sense. But you don't have to look at that.
The radius gets bigger as it goes down in each row, like we call it.
Right. Now, I want everyone to think about this. So, atomic size. What's happening to the atomic size when you're going from left to right and when you're coming from top to bottom? One is easier than the other. So when you're coming from top to down, what's happening to the size? It's increasing, right? When you're going from left to right, why? You're right.
That's what it says.
Yeah, but what if that's wrong?
I know.
What if that's wrong?
It says here, because the nucleus increases.
That's for after this class. I should not have given this before.
Well, see, that makes no sense either, because if the atomic radius is increasing from left to right, why would the atomic size decrease
That's
from left to right?
That's my question.
The nucleus is getting bigger, but the shells is the same as you go across the row.